In this problem, we will calculate the total energy released by steam as it cools. First, we draw the cooling curve of the process and break the problem into 5 parts. Before we begin calculating the heat released, though, we need to find the initial moles in grams of steam present. Using the ideal gas law and then multiplying by the molar mass of water, we see that there are 0.564 moles of steam that weigh 10.2 grams. Since mass is conserved, these quantities remain fixed throughout the problem. The first section of the curve is the cooling of steam. Note that the change in temperature is negative, so the end result will also be negative. The second portion is the condensation of steam. Note that the delta H of condensation is equal to the negative delta H of vaporization, because vaporization is the conversion of liquid water to steam, while condensation is the inverse reaction. The third step, the cooling of liquid water, is much like the first part, just with a different specific heat. To find the heat released by the fourth section of the cooling curve, we need to use the negative delta H of fusion by the same reasoning as using the delta H of condensation earlier. Finally, in the fifth part, the cooling of ice, we use the specific heat of ice to obtain the heat released. Adding up the values we found in each of these 5 parts, we see that the total energy is negative 32.9 kilojoules, which means that 32.9 kilojoules is released. A positive Q value would mean that heat was absorbed. Really, the process of analyzing cooling curves is the same as that of heating curves. Just remember that delta T should be negative and to use the heat of condensation and negative heat of fusion instead.